twofold question that, all right, definitely that what we did yesterday explains how it's derived. The question is that really correct? Can that be that little thing that we are leaving off? Will that add up to a significant amount? So that is incorrect. Stuff like that. So I think I have that in the next slide. Another thing that I brought about is that if you want to see if it is correct or not, you have to compare it with the very definition. Our very definition used the method of cross-section, right? If you look at the cylindrical shell analysis, it's not really the cross-section. So that's one thing. You have to be able to compare what you did in the cylindrical shell method to what you get from the cross-section method. If you can do that, and that justifies it. All right? In general, you can raise a question. There are many different, not just a cylindrical shell out there. In general, there are many different ways of, computing the volume. Then it is still a reasonable question to ask that, how does that measure up to this cross-section, which is the very definition? Is it invariant? Doesn't matter how you do it, it's going to always end up at the same number. That is not automatically guaranteed. So mathematicians usually think about this type of thing. If you think about it a little bit, it's actually a reasonable question, but you see it, so you don't really care about that kind of explanation. Now, that's a fine question, but I believe it. Don't worry. However, when you enter geometry such as four-dimensional geometry, or down there in, microscopic level of size of electron and things like that, you cannot see anything. All you can do there is that you have a principle, and then there's a mathematical way to develop it. In that part, that if you cannot see anything clearly, then the only thing you can rely on is this type of clear thinking. So, because you see this, you kind of believe it intuitively, and they've been using it, so it's okay. Why should I, be skeptical about that kind of thing? But this type of thinking, that you think about whether it's same thing or is it correct, and then think about how to actually go about that question. That idea itself is something that should be introduced even in this level. All right? So I'm going to try. I hope that makes sense. Yeah. And then I think already what I just explained is that this is the correct part, is that what we just did, and then how this one measure up to our very definition. And this was where did that, the other one, I forgot to copy the other picture, but it started like this. Remember this picture? Mathematical method or something at the beginning. Here's an equilateral triangle, and then I divided this side into 4 pieces like that, and draw another equilateral triangle like that. They're all 60 degrees, so this length and that length is always the same. As you can see for that one, if this length is A, you have 2 pieces there, right? If this length is A, you have exactly the same 2 pieces there. So length of this one is exactly 2 times the length of a bottom one. But if you do that a million times, then you're not going to see anything. No measurement technology is possible to go down to this tiny level. But they're always the 2 times. If this is an equilateral triangle with a side length and a length 1, what is the length of this red segment? 2, right? So what's the lesson here? You can't ignore the tiny thing if you add it many times, right? It's exactly 2 times a significant difference. So think about, well, you can actually go back to the cylindrical shell and kind of get a rough measurement on what you're missing and add them all up and do the hard analysis and show that that actually approaches 0. That's one method. So that the sum is close to what we envision as a volume, but you still have to compare that with the cross-section method, right? Because it's not the same method. So I stated like this, and seeing this one is really fun, and it uses techniques of 3 techniques, 1 from Calculus 1 and 2 from ours, right? So I simplified it, A and B are positive number in here. Let me give you a picture. A and B is a positive number. F of x is an increasing function. Increasing function going from left to right, function value rises, right? So, for example, I'm going to make a simple case like this. But there could be a more complicated version of increasing function, right? But this could be a simple one. On AB, n is continuous, so that I can integrate. The function to be able to integrate it, you have to be continuous. And function is always a positive. So all the values are above x, y, x-axis. It's all right? So this is in the first quadrant. And we're about to rotate it around y-axis. Right? Cylindrical shell method. So there's the region. R is going to be this region there. So let me use this fun tool now. Blue. There. How fun. Yes. There's a blue there. This region R is going to be rotated around that y-axis, and the volume is given by that. Right? So what method are we going to use to do that? We're going to use cross-section method, and show that the cross-section method can be rewritten using integration technique to that one. And that will be perfect comparison of cross-section method and that. All right? Let's do this one. So if you rotate around that y-axis, this is axis of cross-section, right? This is a terrible color, so I'm going to change that to something else. We're going to draw what is it? Height segment that is perpendicular to this axis of rotation, right? Correct? So for example, for this part, this I'm going to call C. This is y equals f of x. And that's going to be D. Is that right? Between 0 and D, then 0 and C, I'm going to put this line segment here. Do you know why I put the line segment horizontal like this, even though it seems like a cylindrical method? This is the context of a cylindrical method, but I'm doing cross-section method to the cylindrical method, right? That's what I'm doing. So if this is axis of rotation, putting perpendicular height segment like that is precisely the cross-section method, isn't that right? Yeah. Up to here, from 0 and C, this x-axis here, x-coordinate is A, that y-coordinate is B, right? If you rotate around, do you see that? That's exactly this, where this one I'm going to call P1, that one I'm going to call Q1. That's a P1, Q1. You see that? If you rotate around y-axis, you're going to get this annulus. Correct? So when this one is going from here to there, this x-coordinate never changes. Right? So it's always radius that and radius that. Okay? So volume up to 0 to v, so here's the proof. Volume from 0 to c is going to have pi out there, right? How is this cross-section method looks like? I hope you still remember those. It's been a while. So how does this work? Outer radius squared, right? Pi r squared, right? So what is the radius squared for between 0 and c there? This is where it's, rotated around. What's the first one? Outside is here, right? This is the center. Rotate around. Does the b squared make sense? Pi b squared. That would be exactly this rotation there. And as this variable here changes, this endpoint never changes up to c, right? Fair enough? Yeah. How about inside? A squared, right? That's it. What would be the good variable? It's about this point where this height segment is drawn, right? So what's a good variable for that as it varies from here to there? Letter? D what letter is it? Not dx, right? X is here, right? Yeah, dy is a good letter. Right? We've never done this one before. We never switched this role here, actually did that, but I hope it's alright. Fair enough? Good. That's first bit. We have more to go, right? Hope you see that. Plus, right? Alrighty. So let's do the pi more. Going from where to where? Going from here to there, right? Let's draw line segments again. This time, when you're looking at this position over there, here, and there. Correct? This is P2, and that's Q2. If you rotate this one around y-axis, you get similar thing like this with P2 and Q2 in there. Correct? Alright? So, let's formulate it from where to where? C to D. Y varies from C to D. Pi of outer thing here minus inner thing, right? So what's outer thing there? B squared. Still B squared, it never changes. But you can see inside changes. If you're here, you're using this x coordinate. If you're down there, you're using this x coordinate instead. So it changes as y changes up and down. Right? Okay. So we went to about square something. Not sure what it is, but it's dy. Let's think about it. Anybody get a second? It's all about this curve there, right? What is the equation of this curve? Y equals f of x, right? Y equals f of x. And what you want here is a distance from here to there. That's the distance. That's the radius, right? Is this distance x coordinate or y coordinate here? It's x coordinate, right? You want to know, given y coordinate, what is this x coordinate? That's what you want to know. So if you look at this point there and relate to this equation, and you want to solve this equation for which variable? Y or x? You want to solve this equation for y equals something or x equals something? X, because you want to know x coordinate, right? X equals something, then I know this x coordinate there, and that's going to be the radius. So if it is like not much is given, we don't know what f of x is, what notation do we have to reverse this one? Inverse notation, right? You see that this increasing property allows you to consider inverse easily. If it is up and down, the inverse function requires cut, only here part and that part. But if it's more complicated, you can break this one into regions like this, where it's increasing and decreasing, and separate those problems into pieces like this, where so-called monotone. Fair enough? Yeah. So this one is f inverse of y. That's the radius here. Given y value, the radius of this inner circle, inner rotation, is given by, given y value, f inverse of y. So what goes in there? Inside there? F inverse of y. That's what goes in there. That's a formulation. Now you have to bring your old integration technique and whatever you have from calculus 1 and 2 so far and change this one to that one. Right? Hardest part is this one, of course. And other parts you can see they're all constants, right? B and A never changes. So let's take care of those parts first. What is this one? Pi b squared minus a squared. That's a constant, right? You can factor that out, and there's an invisible one. So isn't that just y here between 0 and c? This antiderivative of this one with respect to y would be just y. 1. So that will be just c there, right? How about this one? This part's easy. Pi b squared times y c to d, right? Minus pi times, then you're left with fy squared dy going from c to d. Fair enough? Let's simplify this one. Is a pi b squared minus a squared. And what is this one? C minus 1. How about this one in here? Plus pi b squared d minus c. Is that right? So is there some cancellation? And no cancellation. Does or not? B squared c? B squared c. Do they cancel? No. So here's the pi b squared minus c minus pi a squared c. Here's a pi b squared d minus pi b squared c. You can see these two cancel, leaving these two part. And this part, I'm going to leave it like this. Alright. So we have these two things left. The b pi b squared d minus pi a squared c. These two cancel. And minus pi times cd f inverse y squared dy. Good? Alright. So how can we turn this one into integral that has f of x in it, not f inverse of x in it? It is first substitution. Okay, so here I'm giving you the substitution. I'm going to use z, since u and y is confusing. Z equals something. What choice do we have, you think? F inverse of y or f inverse of y squared. So I think the first you will definitely try m inverse of y if that's anything. But if that doesn't work, maybe you're going to try f inverse y squared. But let's try f inverse of y. Alright? Here it seems like main variable is y, right? So we're differentiating with respect to y. That's the key. We're not differentiating with respect to x. Is that right? Yeah. So how do you differentiate? This is Calc 1 skill. How do you differentiate this inverse function? The technique is that you write down without the inverse, which is fz in there, equals y. Where you understand z is a function of y, right? Z is written as a function of y, so you recognize it here. Z is a function of y. So when you differentiate, you use the chain rule properly. Okay? So what we're about to do, we want to calculate to do this substitution. Let's call it a z substitution. I want dz over d what? Y, not x. Because we're integrating with respect to y, so therefore you have to be dz dy. This is what we want. It's not immediately not sure what to do, so I switched it like this. Is Calc 1. It's called inverse differentiation, implicit differentiation, and that's the term you've learned in there. So let's differentiate this one, knowing that z is a function of y. Then you enter this one. You see there's f prime of z. If you differentiate left-hand side with respect to y, then you have to multiply something. This is called chain rule. What should we multiply here? Z prime, right? Is a dz dy. That's z prime with respect to y. And the right-hand side is 1, right? Okay. So what is dz dy? Reciprocal of f prime of z. Isn't that right? What? So this is ready now. We just calculated. This has one nice expression in terms of f that's better than f inverse. Good. Unfortunately, this is not in y, right? It's still in z, which is the function. But that's good. I think this is going to switch to z. So let's continue. We have pi b squared d minus pi a squared c minus pi times. This one will be, now this one is called z, so it's a z squared, right? Correct? Times reciprocal of this one, correct? What is the reciprocal of that one? F prime z. Then it changes to dz, right? Okay? You probably know the answer is not cd here, right? If you're switching definite integral in substitution, this must switch too, correct? Okay, let's go back in the graph. When y is c, what is inverse value is a there, right? So that's how it switches. So this is inverse by input. Through the inverse function, you arrive at an output x. Maybe I should have called that one x. That's actually better notation than z, x here. So if I plug in c there, that gets a. So let me put that in there. A there. What is the other one? If I put d there, then get the other value b. I'm going to go back and check. If I stick in d, Through inverse, you get output B value. So they switch like this. And enter, very nice. There's no inverse. Nice variable. There's f prime in there. Okay? Now I want you to stare at this version. Very nice. There's no inverse in there. That's the whole point of this substitution. We want to go there, right? We want to go there. I want to get rid of this f prime. Get rid of that f prime and arrive f plane. Now you switch to Cal 2. Think about what technique do I have to switch this f prime to f of x there. What technique? Integration by part. That's our exercise today. First exercise, you take just that part. I'm going to state it separately. Take that part, do integration by parts. All right? So exercise number 1, amongst this mess, here's the one problem I separated. Use integration by parts to rewrite this integral from a to b, z squared fz prime is there, dz. Well, of course, you have two choices to integrate, right? You can integrate first factor, you can integrate second factor. But our goal is this one here, right? Then you have only one choice to do. So that's our exercise. How was it? I integrated f prime of z, so I enter f plane g, right? And I differentiated z squared, so you get 2z. Right? And I evaluated this one at b and a, to b squared fb, a squared fa. Subtracted, and this is as simple as it gets, I think. Question? Now we go back here and replace this part with what we have found, correct? So let's keep that up there. And now volume V is, I'm going to copy that in here. That's the volume, right? We're working on this volume there. You can see that's the volume starting from cross-section. So our volume, using the cross-section method, is this, right? That's that. And we have pi b squared, d minus pi a squared, c, this is minus pi. I'm going to multiply pi everywhere. Negative pi is a b squared, fb, minus pi multiplied with the positive, pi a squared, fa. Negative pi makes a positive pi, pi ab, 2z fc, dz. You can see we're almost there. This is what we want. You just have to explain this one is a 0 rather than just claiming this one is a 0, right? So let's go back. This is matching nicely, pi b squared, and pi a squared, and pi a squared, right? So what is fb? If you go back to the picture, right there, what is fb? Up there, d, right? So down here, What is FB in this picture? FB is D. What is FA in this picture is C. So pi b squared D minus pi a squared C minus, they cancel and become 0. And become, alrighty. We just proved that the cross-section method yields the same quantity as the cylindrical shell method. Now we have a new way of looking at this guy. Where does 2 pi z come from? And then you thought, oh, that's the circumference. That's not really it. That's really the derivative of z squared. That's where it actually landed in. Now, this is amazing. If there's two different things, this matches like this, and this different analysis is just it's worth seeing it, I think. All right? Fair enough?